This video is going to look at the origins of the universe and consider a couple of key pieces of evidence that allow us to think about the Big Bang Theory. So the Big Bang Theory is an explanation of the early development of the universe. And according to this theory, the universe expanded from an extremely small, extremely hot, extremely dense state. And since then, it has expanded and become less dense and cooler. So you can see the Big Bang at the bottom of this image and the formation of galaxies expanding, moving further apart as time proceeds. So the Big Bang was not an explosion. And in fact, that term was coined by an opponent of the Big Bang as kind of like a joke. Actually, the Big Bang was an expansion of space itself. So our first piece of evidence that we're going to consider is where we link something called the Doppler effect and redshift. So the Doppler effect states that the observed or apparent frequency of sound will change based on the velocity between the source and the observer. And similarly, light frequency will change based on the source and the observer. So if you're getting closer to a source of energy like sound or light, then sound will appear higher pitched and light will appear blue shifted. And if you're getting further away, then the sound will appear lower pitched or the light will appear red shifted. Let me show you a diagram. So this is the sound version. You've got a police car giving off a siren. Observer A has the sound moving towards them, and you can see the sound waves are compressing, and when waves are compressed together, then they are higher frequency, and in sound that is higher pitch. For observer B, the car is moving away from them, so the sound waves are stretched further apart. That means the frequency is lower, the pitch is lower, and if that was light, then it would appear to move towards the red end of the spectrum, which is longer wavelength light. So the faster an object is moving away from us, the greater the extent of this redshift, of this stretching of the light waves. So in this image, the top image shows the light coming from a source. If you move it away, the light, each band is moved to the right, which is towards the red end of the spectrum. And if you move it away faster, the bands move further from their original position. And Edwin Hubble, back in 1924, actually observed that. He observed that the light from every object in space that we look at with the telescope appears to have a spectra as if it was shifted towards the red end of the spectrum. So it has light appears to be shifted to the red end of the spectrum. And he actually showed us that further away objects were moving away faster, so showing an expanding universe. The second piece of evidence that we have for the Big Bang is called cosmic microwave background radiation. And in 1965, two scientists called Arno Penzias and Robert Wilson were trying to use satellite tracking antenna for astronomy. The problem was, though, all they could hear was static coming from space. And it didn't matter where they pointed their antenna, all they could hear was static. So it was clear that the signal had to be some kind of electromagnetic wave because it could be detected by anything that could receive either microwaves or radio waves. So where was it coming from? This radiation, this cosmic microwave background radiation, is actually left over from the gamma radiation released at the beginning of the Big Bang. And as the universe has expanded, those gamma waves, which are really high frequency, very tight waves up and down, they are being stretched. And if you stretch them, they move into the microwave part of the electromagnetic spectrum. So by studying this cosmic background radiation, scientists have discovered that it is pretty much uniform all over the visible universe. There are fluctuations, as is shown in this image below. So some areas are more dense in microwave radiation and some are less dense. And this is areas that have seeded galaxies as matter had come together under their own gravity, which is also part of predictions people have made. So the Big Bang Theory is the best model used by astronomers to explain the creation of matter, of space, and of time, and it happened over 13.7 billion years ago. Now, the Big Bang Theory is our current scientifically accepted explanation of the origin and expansion of the universe because of all that evidence which supports the theory. And we've just looked at 2 pieces, and there are others that are more complex to talk about. Here are some of the observations and the advances in theoretical thinking and mathematics that have contributed to our Big Bang Theory being the best explanation that we have at the moment. Around on the outside of this timeline, this curved timeline, are little pictures. These are actual observations starting way back in the 1920s when galaxies were confirmed and observed to be receding away from us and therefore having an expanding universe. That was Hubble. And then we've got cosmic microwave radiation in the mid-1960s being detected accidentally. And then we've got things like rotating galaxies being observed, giving ideas about dark matter, cosmic microwave background radiation being measured by satellites, supernova showing that the universe is expanding at even faster speeds far away from where we are, sort of in the furthest reaches of the galaxy, and so on. And then on the inside of this timeline, we have the thinking and the theories and the mathematics that people have projected and thought this is happening, and ideas that have been kind of cemented over time. So you can pause the video and zoom in to have a look at some of these ideas. And we'll finish on this image. This image shows the history of the universe, starting with the Big Bang on the left, and it's a timeline going from a very small amount of time immediately after the Big Bang, going through to kind of where we are today. This is not a linear timeline. So here, for example, where we see the appearance of nuclei, so we've got hydrogen and helium nuclei, that's at 100 seconds after the Big Bang. And then our next line here, where we start to see visible atoms actually appearing, so hydrogen and helium as whole atoms with electrons associated with them, that is in the tens of thousands of years after the Big Bang. So you can see that these jumps are not linear. And this is where we are today, where we have materials and we have galaxies and we have nebulae and we have atoms. And you can see all the way from the beginning, you've got these little squiggles. These are electromagnetic radiation. So this is the gamma radiation I was talking about, that as the universe has expanded, it has stretched and become cosmic background radiation. So there's lots to unpack in here. You can have a look at the key down here and see that these are the things we know about. So protons, neutrons, electrons in here and in here. But back here are the bits that make up protons, neutrons, and electrons. So things like quarks, gluons, bosons, etc. If you're interested in those sorts of things, studying physics to a high level will be something for you. So the theory of the origins of the universe and the expansion of matter and time, energy, the Big Bang Theory.